Here we have a 500 kilogram cannon that fires a 12 kilogram cannonball at a velocity of 300 meters per second. What's the recoil velocity of the cannon? This is about as simple as a conservation of momentum problem gets. The momentum before has to equal the momentum after, so that means the mass times velocity of each object before has to equal the mass times velocity of each object after. Nothing's moving initially, and you have everything else but the velocity of the cannon, so plug it in. A tiny bit of algebra later, and you are done. If you're dumb enough to drive a Yaris in Western New York, unfortunately, you're gonna eventually hit something rather large. The mass of this deer is rather unrealistic, but it makes a good problem. Let's do it. Yet again, the initial and final momenta are equal, but in this case, it's an inelastic collision, so they stick together and you can treat them kind of as one object afterward and combine their masses. The deer is at rest and we know everything else but the final velocity of the entangled mess, so plug in and solve for it. Here's a festive problem. Can a red-nosed reindeer really fly if you hit it hard enough? In this problem, the collision brings the truck completely to a stop and transfers all of the momentum to the reindeer. Finding out is as simple as accounting for the momentum of the truck and the reindeer before and after the collision. Plug in our numbers and Old Red goes down in history at 7,200 meters per second, about 20 times the speed of sound. This problem started as a what if a student asked me my first year of teaching, and I've kept it ever since. The answer, of course, is nonsense, and it takes a little thought to figure out why. Calculate the kinetic energy of the truck and the deer before and after, and you'll see it. Rocket science is hard, but momentum and impulse can make it a lot easier. Here's a rocket that's traveling at 50 meters per second when it fires its thrusters and gets 100,000 newtons of force for 5 seconds. But in the process, its mass decreases as it burns fuel. This would be impossible without calculus trying to use Newton's laws, but with momentum and impulse, it's downright easy. Initial momentum plus or minus impulse equals final momentum. Momentum is mv, impulse is force times time. Solve it, plug in your numbers, and this thing sped up a whole lot. Two-dimensional momentum problems are just like two-dimensional kinematics problems. You separate the x and y, treat them independently, and then combine them back together as vectors using tip-to-tail and the Pythagorean theorem. This is an inelastic collision with the truck not moving in the x direction. Solve it, plug in, and get 13.125 I-hat meters per second. Same thing in the y direction, only the car isn't moving. Solve it and plug in to get 9.375 meters per second j-hat. These are, of course, vector components, so combine them using the Pythagorean theorem to get 16.1 meters per second. Then use trig to get the angle of 35.5 degrees. The ballistic pendulum was invented in the 1800s to determine the speed of bullets, and is a classic physics problem. First, you have a bullet collide with a wooden block that is attached to a rod and free to swing. It swings up to a certain angle. You can then use that angle and the mass of the block and bullet to calculate the speed of the bullet. Step 1 is to apply conservation of momentum to the collision between the bullet and the block. The bullet is moving, the block is not, and afterward they are stuck together. Solve this for the speed of the bullet, but we don't know VF, so we've got to move on. Step 2 is to apply conservation of energy to the upward swing. The block bullet earth system has kinetic energy at the bottom and potential energy due to gravity at the top. We've done this a gazillion times, the masses cancel and you get V equals the square root of 2gh. Step 3 is to determine the height of the pendulum, and we've done this before too. With a little bit of trig, we can find that h equals L times 1 minus cosine theta. Plug that into your formula for VF, plug that in for your formula for V0, and you get your answer, the combined masses divided by the bullet mass times the square root of 2gl times 1 minus cosine theta. Bumper cars conserve momentum too, so we can take the momentum before and set it equal to the momentum after, accounting for each of these two cars. If we just plug in our numbers and solve, we run into a problem. Momentum is a vector, and these cars are going in opposite directions. With that negative sign in place, we can solve to get v1f equals 1.5 v2f. This is an elastic collision, so kinetic energy is conserved. And after a bit of algebra, we get another equation relating the final velocities. Plug the first into the second, and we get v2f is plus or minus 2 meters per second. There's no way cart 2 kept the same velocity after the collision, so we reject the negative answer. Plugging that into the red equation gives us v1f equals minus 3 meters per second. This next one is a bit of a monster. We saw playing with carts that in an elastic head-on collision, the carts will exchange velocities. Let's prove it mathematically. This is not easy. We start with conservation of momentum and then group-like terms so we can factor out the mass. Let's call this equation 1. This is an elastic equation, so we can do the same thing with kinetic energy, group-like terms, and factor out the mass. Let's pause and look at this thing for a moment. On each side of that equation, we have a difference of squares, so let's factor that. And let's call this equation 2. Now here's the fun part. Let's take the entirety of equation 2 and divide it by equation 1. Almost everything cancels. And after a little rearranging, what we end up with is that the difference in speeds before the collision is equal to minus the difference in speeds after the collision. So what does that mean? Put yourself in the reference frame of one of the blocks. From your perspective, you're sitting still and the other block is coming in at a speed v. After the collision, it's moving away with a speed minus v. That can only happen if the two blocks exactly exchanged their velocities. The one sped up and the other slowed down by the exact same amounts. So Tarzan has been poisoned and Jane needs to rescue him. She's standing a meter higher than he is and she has a rope, but she knows she doesn't have enough energy to swing down, grab him, and swing back up. That would be impossible unless she got a running start. How fast does she need to run? This problem has 3 parts. The swing down, the collision with Tarzan when she grabs onto him, and the swing back up. So it shouldn't surprise you that we have to do 3 separate equations. With her running start, she has kinetic as well as potential energy at the beginning, and that all converts to kinetic energy when she reaches Tarzan. We can plug in our energy equations, cancel her mass, and then solve for the velocity she needs at the top in terms of the velocity at the bottom. The collision with Tarzan is of course governed by conservation of momentum. It's perfectly inelastic, so combine their masses after the collision and solve. This third velocity is how fast they need to be going to make it back up to the top, and we can use conservation of energy to find that. Kinetic energy turning into potential energy due to gravity ends up with v equals square root of 2g delta y, which we've done a million times before. Plug v3 into equation 2, then plug that into equation 1. Square it, group like terms, and simplify, and you are done. Somehow I think Jane would just run as fast as she could and hope for the best. Glancing collisions, like you might get with hockey pucks or billiard balls, are another multi-step problem. And like the previous one with Tarzan and Jane, I think if you were asked this on the AP exam, or say one of my tests, it would say write but do not solve the equations necessary to find whatever variable you're looking for. So let's do things that way. Our first equation is conservation of momentum in the x direction. If we cancel mass and find our component vectors, we end up with 3 unknowns. We need at least 2 other equations. Our next one is conservation of momentum in the y direction. Cancel mass and find your component vectors, and we end up with the same 3 unknowns. We're making progress. Our final equation is conservation of kinetic energy. We can cancel the 1/2 m's and end up with a velocity equation that contains 2 of our 3 unknowns. 3 unknowns, 3 equations, we are done. It's worth noting that solving this system of equations algebraically is really hard, and I'm never, ever going to ask you to do it. But I would absolutely ask you to write out the equations like we did here.